So today we're gonna start talking about things that are obviously black holes versus active galactic nuclei, which we'll talk about next. This is really what we're talking about now, which are black holes, but it's not obvious that they're black holes until you take apart what the actual objects are. So today, and I'm gonna start AGN today after I talk about this. I was supposed to post a reading for today, but I forgot. And I was also intended to post the numerical homework for today, but I forgot. So there's a reading due tomorrow. Sorry for giving you short notice on that. It's about black holes. So it's pretty fun. And again, the readings are super low impact, so if you miss it, not a big deal. But please try to get, at least put your eyes on this stuff. So there's a reading due. I put up all the rest of the readings for the rest of the semester, so they all should be up. I'm going to put up all the numerical homeworks for the rest of the semester after today. None of them are very long, but if you haven't coded before, it might be tricky. So I'll have office hours. I'm not going to have office hours for everyone because I'm going to make 2 of them due in 1 week. So we'll talk about that next week. But none of them are super painful. So those are coming, and I just didn't get on the stick of assigning them. So we'll do those in the second half of the semester. Okay, so we're going to talk about AGN, which are active galactic nuclei, and then we'll talk about clusters of galaxies, and then we'll be done for this semester. So that's where we're going. So now we're going to talk about things that are obviously black holes. So we're going to talk about what's a black hole, and if they're real or not, and then we'll talk about how you actually see a black hole. We'll talk about the first black hole, Sagittarius star. We'll talk about Cygnus X1. We'll talk about supermassive black holes. We'll talk about LIGO. Oh, we'll talk about other stuff too. This outline slide I didn't update, huh? Anyway, okay, what's a black hole? First things first. The energy that you have leaving the surface of an object is gm over r. That's the energy, that's the binding energy that you have. That's the gravitational energy that you have binding you to the surface of the object. Now that object could be an asteroid, it could be a tiny little planet, 13.5b. What was the little princess planet's name? I forget. Anyway, whatever it is, this is the escape velocity. So the velocity that you need to leave that is just 1/2 mv squared, right? So, so m cancels out from both sides, and you got the force, and you've got the energy, and you've got the energy of the thing that's leaving. So 1/2, so gm over r is a gravitational energy. 1/2 mv squared is the energy of an object. So m cancels out on both sides. So you're left with the escape velocity is just 2 gm over r squared of all that. So now if the escape velocity is the speed of light, then we know that nobody gets to go faster than the speed of light, so that's the biggest an object can get. So that gives us the Schwarzschild radius is 2 times g times the mass of the object divided by c squared. All of these are numbers except for m, so we'll just pretend that's a solar mass, and we'll get a number of 3 kilometers. 10 to the 5 centimeters is a kilometer, right? So 3 kilometers times the mass in solar masses. So what would the Schwarzschild radius of the sun be? 3 kilometers. How far away is 3 kilometers? I mean, is the other side of campus 3 kilometers away? Like, maybe?
Maybe over.
I think it's like
It's around 2
Yeah.
or 3.
So we're talking about something that's basically the size of campus,
Yeah.
maybe a little bit more. I probably can't. I mean, my house is further than 3 kilometers away, and I don't live very far. So not very big, but you have to cram an entire solar mass into that space. So it's a very, very, very high density. It's like a little bit more than 1/2 mile. Okay, this looks like virial theorem, right? V squared equals gm over r, but there's this 1/2. Why is there 1/2? I'm curious what the hint says, but I don't want to reveal the hint. So where's the 1/2 go? What's the difference? Oh, yeah. Well, here I'm talking about energies. But when we're talking about a virial theorem, we're not talking about energy balance. It's force balance. That's the difference between the 1/2. So virial theorem is all of my forces all kind of statistically average out to be something regular. This is just about the energy, which introduces a 1/2, which matters, but not a ton. But the difference matters more than the 1/2 does. The fact that we're talking about energies here and not forces. But small differences is just a 1/2. So the Schwarzschild radius is 3 kilometers times the mass of the object in solar masses. So what do we? So they come in 3 different flavors. So there are stellar mass black holes that are up to about like 10-ish. These aren't hard boundaries. These are ish boundaries, but you can write them down anyway because they're not bad. So between 1 and 10 solar masses are stellar mass black holes. So these are black holes that are formed from stars. Bigger than that, we have intermediate mass black holes, which are like 10 to a lot of solar masses. And we don't really know where these things came from. When I first started giving this class, I said we're not going to find very many of these. There's a black hole desert between like 10 and like 100,000 or a million solar masses. This is the story that I was told when I was coming up. And I was telling my students that there aren't any intermediate mass black holes. Then we turned on LIGO, and the only thing it sees are intermediate mass black holes, which we didn't think should exist. So, anyway, you turn on a new camera and you see new things. So the intermediate mass black holes. So if you want a 100 solar mass black hole, you can't form that from a star. A star that's big enough to make a 100 solar mass black hole in its center is going to be way bigger than 100 solar masses, right? When those things fail, they go straight to making positrons, and they just explode. They don't. So when you get something that's bigger than like 1,000 solar masses, they fail in really weird ways and can't make black holes. So you can't make a 100 solar mass black hole straight from a star. A 100 solar mass star makes a like 10 solar mass black hole. So you need something really, really big. Why? Because this process of forming a black hole is kind of complicated. And if you think about, did you guys go to the circus?
Yeah.
Did you guys go to the mechanics room? I know you were in the mechanics room. I know I saw you. So there was this one thing that's these set of 3 discs, and you drop them, and because of a momentum exchange, the first one doesn't bounce, and it just transfers all its momentum to the top one, which injects like crazy, right? It's a really fun thing because you can get these little things to hit the ceiling and then hit your circus goers in the face because it flies everywhere because it's got a lot of velocity, because it bounces because it steals all the momentum. So now if you scale that up and make it 3D and make it on fire, when you have a star, it's got a center. All the burning happens at the center where the temperature and the density are high. That's where all the support comes from. So when that fails, then you've got all this stuff that's going to rain in. So we need the temperature to keep the star up. When the temperature goes away, then the star falls down into the black hole. Some of it, if it's big enough, some of it will stay in, just make a black hole, but then a lot of the stuff bounces off and becomes an explosion. There's a huge number of neutrinos that get released in this process. The whole process is super interesting. I'm not going to get into it, but if I have 100 solar masses, only part of it is going to actually not bounce off and get blown up into the rest of the cosmos. So intermediate solar mass black holes have to come from mergers of a bunch of things. So I've got to pack a whole bunch of 10 solar mass things together to make a 500,000 solar mass black hole. So we're not sure where those things come from, but we see them all the time. Now, the most populous that we have seen, but probably not the most populous, are supermassive black holes that are between 10 to the 6 solar masses and 10 billion solar masses. It's a very small range, but these are really, really big objects. So let's see. So where do they come from? So this is kind of what I said. So stellar masses come from stars bigger than 8 that run out of fuel. Sometimes there's a neutron star and sometimes there's a black hole. it's weird. It's not obvious which one does which and when. So there's a really cool plot from this really massive paper on stellar endpoints, and he ran a suite of simulations using Mesa, I think, where he ran the code up until the end and decided what the endpoint was going to be. And as he increased the mass, it went from neutron star to black hole to neutron star to black hole to neutron star to black hole to neutron star to black hole. So it's kind of oscillates. It seems chaotic. What the endpoint is not determined solely by the mass. It's not clear. So sometimes it's a neutron star, sometimes it's a black hole. That's the only thing I care about from this. Bigger than 8 solar masses. Intermediate mass black holes have to come from mergers somehow, but there's a lot more of these than we think there should be, so that's a problem. And then supermassive black holes, okay, supermassive black holes grow like this, an exponential. What do you know if I tell you that something evolves like an exponential? What do you know about that thing? It means it's growing and the growth rate is proportional to the value, right? So when I have a black hole with mass m, the rate that it can grow is proportional to m, which means that its growth is exponential. So what's an exponential look like? Like that. So we need the slope. So an exponential looks like m naught e to the t over tau, where tau is the time scale and m naught is how it started. So if m naught, the seed, is big enough and tau is short enough, then we can make black holes of whatever size we see. But we'll see that to get a 10 billion solar mass black hole at a redshift of 7, m naught has to be really much larger than we think it should be, and tau has to be much faster than we think it should be. And I'll show you what both of those things should be. So we're not really sure how these things get so big because it's curious. We'll talk more about that later. We'll talk about black hole growth in a second. So the important thing we want to talk about is how to measure masses. How do we actually measure the mass of a black hole? So this is a summary of all the ways that we've talked about to measure masses so far. So we talked about things that are easy to measure for astronomers as brightnesses and radial velocities. Those are easy to measure. Things that are hard to measure are distances and masses. And masses are hard because distances are hard. But so to measure the mass of a thing, we can use stellar spectra. That's good for stars, but not galaxies. That doesn't work. You can use binary stars. If you got 2 stars, I don't need you to do that. The pair gives you the orbital dynamics, and the orbital dynamics gives you the mass of both objects if you can measure the actual orbit. Rotation curves of galaxies, which uses virial and Keplerian assumptions. Velocity dispersion of things. Yeah. Oh, you're just... the cluster scaling relations, which we haven't gotten to yet. We'll talk about how black hole or galaxy clusters scale. And then there's a lot of different ways to measure the mass of black holes. And I'm going to talk about these more in detail, but I'm going to put them all up now. Here, let's make this so that I have the whole slide. So if a black hole is in a binary, you can measure its mass that way by the binary dynamics. If it's in the center of a galaxy, you can measure what the population of stars are doing nearby. I'll show you this, what I mean by that. Gravitational waves give you the mass directly. If you can see it, the size gives you the mass directly. Why is that? How are the mass and the size related? It's a Schwarzschild radius, so you know that mass and size are linearly related. Let's talk about that for a second. If I have a solar mass of soup, and then I add another solar mass to it, the radius, okay, so the mass is rho r cubed, right? So the radius is the mass over the density of the 1/3. So assuming the density doesn't change substantially, if I double the amount of stuff in my star, say this is a sphere of whatever, goo or stars or whatever, the radius should go up like the mass to the 1/3. Make sense? But black holes, the radius is proportional to the mass directly. This is a very useful thing for us. It also tells us that black holes are really, really stiff. As you add more mass, they get bigger fast. The Eddington luminosity, which did hopefully talk about Eddington luminosity at all? No? Okay, sweet. Reverberation mapping, which is one of my favorite things. I'll tell you why. The M sigma relation, which again I'll explain in the broad line region versus continuum luminosity, none of which I have explained. So there are several ways to measure the masses of black holes. Some of them are direct, like binaries and stellar kinematics and the gravitational wave chirp and looking at it, and some of them are not. The Eddington luminosity is not a direct way of measuring the mass of the black hole, but it is a very good measure of the mass, and it's the most common one. So we'll talk about all these in detail, but let's actually look at the black hole first. Here's one. So watch what's going on here. So this is an image, very carefully taken film of the stars at the center of the galaxy. So we're going to zoom in on these stars, and we're going to watch the orbits, and we're going to plot them. This big one is called S2. It's a very special star. So you see what it did? It hooks around nothing. There's nothing there. Watch. I mean, nothing's there. Watch it hook around. Watch this guy go. There is nothing here. But clearly there's something very large there. But you can't see it at all. From the dynamics, so do I have that slide up? Oh, I don't. I thought I had a different slide. That's what I get for changing my slides. From the orbital dynamics of all of these stars, there's about a half a dozen stars or a dozen stars that are orbiting the black hole at the center of our galaxy very closely. And because we live in a nice universe that's nice and handy and doesn't have an active black hole, we can see it. So we can see the stars going around the black hole, and we can measure general relativity. We can measure the mass of the black holes. We can measure the dynamics really well. And this is 4 times 10 to the 6 solar masses is the mass of the black hole here. And that's the black hole at the center of our galaxy. Yeah.
What do you mean by active black hole?
I'll explain that in a second. When there's a lot of stuff nearby, the black hole accretes. It absorbs stuff. And then they outshine galaxies. You can, when they start to feed, when a black hole is feeding, it becomes active. And when it's active, you can see them clear across the entire universe.
So, is it like it can only be active in the beginning stages, or it just depends on what's near it?
Yeah, good question. It depends on what's near it. So it depends on whether or not it gets to feed. If there's stuff nearby, it'll eat it.
Okay.
But if there's not, then it can't. And that changes throughout the whole course of the history of a galaxy. So sometimes a galaxy black hole can be active and sometimes not. Our black hole is not doing anything interesting right now, which is good for us. So I'm getting kind of ahead of myself talking about active galaxies. Let's talk about things that are actually black holes, things that are obviously black holes. So the Nobel Prize in 2020 was given to Roger Penrose for predicting black holes, and Reinhard Genze and Andrea Getz for actually studying them. And I actually called this on Twitch screen, but I couldn't remember their names, so I don't really get to claim credit. But I was doing a gaming thing where I answer science questions and play video games. It's super fun.
Watch that over race.
Was that?
Yeah.
Oh, did you really?
Yeah.
That's awesome. So anyway, Ken's a good friend of mine. I played Battletoads, which is one of the greatest games, really badly. And the Nobel Prize was coming out just the next day, so it was like, who do you think is going to win it? And I was like, no, well, nobody's, like, astronomy doesn't really come up for the Nobel Prize too often. But if it did, I said it's the black hole people, but I couldn't remember their names. So anyway, they won the Nobel Prize for this and other things, but this is because they figured out a way to take pictures of these stars. This is very, very, very difficult measurements to make. They require adaptive optics. Do you guys know what adaptive optics are? So, I used to have it in this slide too, and I took it out. Basically, on the really big telescopes, the atmosphere is in the way of the light. In all telescopes, the atmosphere is in the way of the light. But if you want really good angular resolution, then the atmosphere is really in the way because the atmosphere is fluctuating and it moves your star around. So what they do is you've got your image of the star. Oh, I should, while I'm dancing around. So the atmosphere is moving the image of the star on my telescope. So if I've got my telescope here, the atmosphere wiggles the star around, and the point of the star moves around on the on my sensor. So what I can do is just move my sensor, right? It's pretty brilliant. So as the atmosphere moves, I move the sensor to catch up with it, and this works actually super well. What they do is they take these really high power sodium lasers. Here's the Earth. Here's the telescope. Here is the upper atmosphere. There's a layer of sodium up in the upper atmosphere. Now the violence in the atmosphere is in the lower atmosphere, the turbulence. So what they do is they shoot a laser and they make a fake star in the upper atmosphere by shooting it with a laser and making all of the sodium light up in the upper atmosphere. It's called a laser guide star. Now, I know what this star is supposed to do. It's not supposed to move because it's a point in the atmosphere. But it does move because all this stuff wiggles the light. Now, I have a moving mirror here. And I just tell the mirror, keep this star still. Do whatever you got to do, keep that star still. And it will correct all of the motion of the atmosphere. It's very cool. So this is a technique called adaptive optics. And it's not the whole mirror. So Keck is an 8-meter piece of glass. It's 64 pieces of glass, but it's a giant thing. What they move is a little mirror at the end. So there's another mirror that makes a reflection right onto the sensor. So they move this one, which is little. It's only this big, so it moves around real easy. So Gens and Getzel were instrumental in making adaptive optics work so that we could actually take these pictures, because you need to understand the positions of these stars incredibly accurately to be able to do the measurements. So they won the Nobel Prize in 2020. In 2017, the Nobel Prize went to Kip Thorne and Rainer Weiss and Barry Barish for LIGO. So LIGO is one of the coolest devices that human beings have created, and I'll talk about it in a minute. But basically, it uses lasers to measure the stretchiness of space to within the distance of a proton. Not just a proton, a thousandth of a proton. Very, very, very sensitive.
What do you mean by stretchiness?
Stretchiness. So, okay, I'll talk about it for a second. So LIGO is 2 lasers. So there's a laser source here. It bounces off. The laser bounces off a splitter and goes this direction. Bounces off of a laser, off of a mirror. Not just any mirror. This is an incredibly complicated mirror. And then some of the other photons go off and bounce off of this mirror, and they come back. They both come back, and they get collected in this incredibly precise brightness measure. And what the 2 photons do is they interfere. So I got these 2 photons. I built them so that they were in phase, and they'll measure the distance of these 2 lines. So if one of these gets a little longer, then I've got my photon 1 and my photon 2. If one of them gets a little longer, then you get a little bit of interference. So the peaks don't match up, so the brightness doesn't add completely to the top brightness. And you can measure that. So when a gravitational wave goes by, gravitational waves are quadrupoles. So when one side goes out, the other side comes in. Think about like stretching a sheet, like a piece of paper or a piece of rubber. If you pull on it, it gets skinnier. Space does that. Space is not compressible. A lot not compressible. It's not very bendy either. It's very stiff. So when you have one of these gravitational waves go by, one side gets longer and the other side gets shorter, and then they switch and they oscillate like this. And this detector can measure the distance, the difference in the lengths of these two 4-kilometer arms to within a fraction of a proton by measuring the brightness of the interference fringes incredibly accurately. I got some pictures of LIGO, and I'll show some more results of that in a second. The third Nobel Prize for general relativity stuff is actually the first one given for general relativity ideas was in 1993. The Hulse-Taylor pulsar is a pair of pulsars that are slowly getting closer. They can measure the orbital dynamics of the pulsars really well because they're pulsars. And because they're neutron stars that are very tightly orbiting each other, they're radiating gravitational waves like crazy. Because they're radiating gravitational waves, they're losing gravitational energy. Losing gravitational energy means they're going down the potential well. That means they're getting closer. That means the orbital period is spinning up. That makes sense? So they're spinning, radiating the energy away, and they're slowly radiating that energy away. And eventually they'll in-spiral. So they've been measuring this pulsar. So this is the period of the pulsar versus years. So from when they discovered it in 1973 till recently, you can see this. The period is getting slower and slower and slower, or it's getting faster. Which period shift is getting shorter.
Closer and they get faster.
Yeah, the period is going down, so that's okay that it's negative, right? Because the period goes down. So anyway, that's not something we're going to talk too much about. So how do you see black holes? So you can see them in binaries. You can see them from the X-ray emission or from their kinematics. So there was recently a black hole that doesn't have any X-ray discovered. It's the closest black hole to us. It's only like 1,500 light years away, which is pretty close. The kinematics of the galaxy, you can see them from the AGN, and now we have these two new methods. You can use direct imaging or gravitational waves. I'll talk both about these in a second. Let's talk about a little bit more about history. So this is the first radio telescope. And this, I think, is Carl Jansky. So Carl Jansky worked at Bell Labs, which is the telephone company. And Bell Labs did an enormous amount of good for science. They were a research group that did all kinds of things like invent the transistor. Massive amounts of really cool things came out of Bell Labs, including radio astronomy. So they were trying to do wireless communication using radio waves. And they needed to understand the source of the noise of radio waves, so they just put Carl out in a field with his big radio telescope. How is this a radio telescope? So this is a big square of wire. And when a radio wave goes through it, Lenz's law says there's going to be a current. Because a photon is an electric field and a magnetic field. The magnetic field goes through and excites a current in the loop. You can measure it. It's also on wheels, so he can point it wherever he wants. And then the planet moves, so he can point it wherever he wants, up and down. So one of the things that he did, so he classified the noise that you can see in the radio. One of the things that he did was he found one source of noise in the middle of Sagittarius that was always there and never went away and clearly came from outside the planet. He didn't know it, and I don't know, I should actually look this up when it was really fully confirmed that Sagittarius star was a black hole. I don't actually know. It wasn't then. It was many years later that it was actually confirmed to be a black hole, but he knew that it was something weird. We then go on to name everything in radio astronomy after him. He did no more radio astronomy because they wouldn't let him. And then he died in his 30s, which is kind of sad. So shortly after that, and this was 1932, long time ago. And Sag A star, maybe I haven't said this out loud. That's Sagittarius, shortened. Sagittarius is a constellation. Sagittarius A is part of the radio map, and Sag A star is a part of the radio map that's really, really bright. So it's an observational designation of, hey, there's this weird radio source, and it has become the name of the black hole. So the name of the black hole at our center of our galaxy is Sag A star. So that was the first one that we've ever seen, and Carl Jansky saw it. Shortly after, they started sending suborbital sounding rockets. So these are rockets that go up above the atmosphere and come right back down. So like you launch it in New Mexico and it comes back down later in the day further west in New Mexico. You need a rocket because X-rays don't go very far in the air before they turn into something that's not an X-ray anymore. So they get absorbed and they do stuff. So they shot this X-ray telescope way above the atmosphere, and they looked at a couple of things, and they found a bunch of X-ray sources. They found some in Cygnus the Swan, which we'll talk about, in Sagittarius, which we have talked about, and Ophiuchus, and I think there were a couple others. Ophiuchus is a big star-forming region. Why is a star-forming region a good place to look for black holes?
Supernovas.
Supernovas, right. So where there's lots of active star formation, you have lots of explosions, you have lots of stellar death, you have lots of stellar corpses. So star-forming regions are a good place to look. Ophiuchus is one of my favorite star-forming regions. So in the 60s, they found several. Cygnus X1 is one I'll talk about for a minute. So this is the companion star. The black hole is not pictured. Next to it. So what we can learn is the black hole is 14 solar masses, and its companion star is an O star, and that's this dude here, is 19 solar masses. So it's close enough that we can get parallax distances with VLBA. Have I talked about very long baseline interferometry? Let me do that for a second, because I'm going to need it later. So let's divert VLBA. Let's talk about the diffraction limit for a telescope. You guys learn what the diffraction limit of a telescope is? I'm going to teach Intro to Astro in the fall, and I really wish that I had been keeping a running list of, did Hoflick talk about X, Y, and Z, and all the things where you're like, no, I need to go write down and make sure I talk about them. I should have been taking better notes. Okay, so diffraction limit. Let's talk about this for a second, and I got to look up one number. Bear with me 1 second, because Squirrel Brain is not letting me. Because it's like 2 minutes, 2 millimeters. Come on, internet. Where is that number? Anyway. Okay, so when you have a telescope is a hole. No, it's not. It's a mirror. It's a hole enough. Light comes and hits this thing and then reflects back. And there's an edge and then light coming through this. So that's effectively a hole with light coming through it, even though, right? So what do we know about when light goes through holes? When I have a slit and I have photons going through it, what's it do? Do they just go straight through and make a stop? What?
It creates a diffraction.
Yeah. Why does it make a diffraction?
Because it's like waves.
And waves do what? Interfere. And then interference depends on the orientation of the two bits of the photon. So we get an interference pattern. So we get a bump here, and then we get a minimum, and then we get another maximum, and then another maximum. Right? This is single slit diffraction. You could do it with two slit diffraction, which makes more sense kind of aesthetically, but because when you have one slit diffraction, then you're actually looking at a photon interfering with itself, which bothers me. But if you just let one photon through at a time, you get the same interference pattern. So we get this interference pattern. So this, in 2 dimensions, if I just have a hole, then I have rings, where I've got a bright spot and a dark spot and a bright ring and a dark ring and a bright ring and a dark ring from the same physics. Oops. This is called the airy disk. This is the important bit. The rings don't matter. They're low. But this is pretty small, and yeah. So the size of the airy disk is going to be proportional to the wavelength of one of the wavelength. As lambda goes down, the disk goes down times like 2 millimeters. Okay, I'm putting that in quotes. Don't write that down. So the size of the disk depends on the diameter of the telescope. I forgot to pull up a lecture on diffraction limited systems, so and I'm not able to invent one on the fly like I want to. So the size of the disk depends on the diameter of the telescope and the wavelength of the light that you're looking at. Does that make sense? So if I have a bigger telescope, the airy disk gets smaller. And if I use a longer wavelength, the airy disk gets larger because I've got a larger wavelength. Does that make sense? So it only depends on the diameter of the telescope. If I cut a hole in the middle of the telescope to, say, let the light go through, it does not change the angular resolution of the telescope. I could cut a really big hole, and it does not change the angular resolution of the telescope. The only thing that sets the angular resolution of the telescope is the diameter and the wavelength. The rest of the telescope in the middle is good for collecting photons, so you can see dimmer things, but you can't see smaller things. So now we take this idea and say, okay, the middle of the telescope only matters for photons. The edge of the telescope is where you get resolution. Let's make 2 telescopes and put them on the other sides of the planet. So now I can use the whole planet as my telescope. So there's this really cool thing called very long baseline interferometry, where I take a radio telescope and another radio telescope, and I tie them together in a computer, and I make a telescope that has a baseline that's very long, so the resolution gets really, really good. Does that make sense? Now, it turns out they don't actually even have to be connected. As long as they have a good enough clock, computers are fast enough that you can write down the entire waveform of the photon as it comes in. Because a gigahertz photon, you can just sample it and sample the entire electric field for the thing. So all you need to do is have a really good clock and write it all to tape. Then I have all the data from this telescope and all the data from this telescope, and I ship them to Virginia, and we take those 2 bits of tape and we line them up and we make one picture. Does that make sense? So this is called very long baseline interferometry, and it's a very cool thing. So there's, so this is the technique. There's one called the very long baseline array, and it uses Arecibo in Puerto Rico and telescope in Hawaii, some in Chile, some in New Mexico, some in Europe. I have a picture coming up. So there's radio telescopes all over the planet that gives us a telescope that's the size of the planet. That gives us incredible angular resolution. So with very long baseline interferometry, we could get the distance good enough to actually tell that this is a black hole. So this was discovered in the 60s, but it wasn't until 2011 that Kip Thorne actually said, and Kip Thorne, remember, he's the black hole guy. He got a Nobel Prize for seeing black holes. He didn't officially say that he believed that this was a black hole until 2011, which is much later than its original discovery. So why X-rays? Let's talk about X-rays for a second. I'll come back to very long baseline interferometry in a second. Let's talk about X-rays for a second and why we have X-rays. So if I've got a star, it's got some atmosphere around it. Remember, stars are a black body plus an atmosphere. The atmosphere matters. I don't have any black chalk. That would be problematic. We'll use blue. So this light, this atmosphere isn't very well attached to the planet. No, I want to be on that one. Oh, I was on the wrong one before. So the atmosphere isn't very well attached to the planet. So if I've got a black hole, stuff can find its way onto the black hole. Right? It doesn't tell me why X-rays, though. Well, about my gravitational potential for the black hole. Gravitational energy is negative. You can rescale it so that it's positive because you want potential energy to feel like a positive quantity. But gravitational energy is negative fundamentally. This has a lot of far-reaching consequences. Namely, as I get closer to the object, I get more negative energy. Right? That energy's got to come from somewhere. And it comes from accelerating the particles. So if my energy is 0 up here, I get a big negative value of my gravitational energy here. I have to have a big positive value of my kinetic energy to offset that.
Would that be the X-ray, the big energy?
So what happens is the gas gets heated like crazy. So it falls down the well and gets heated like crazy. And when the temperature gets above 1,000,000 Kelvin, then it starts to radiate in the X-ray. Really, probably 5. So you get this crushing effect as stuff falls from the O star onto the companion, and then it emits X-rays from around here. Does that make sense? And angular momentum makes sure it's a disk, which is a thing that we'll not talk too much about. Angular momentum is an interesting problem in these systems. I think I talked about all those things again already. Okay, so measuring the X-ray luminosity and the binary details of a pair of stars is a good way to measure stellar mass black holes. If you want to measure a supermass black hole, we want to do the same thing. So like this guy here, here's M84. It has a supermassive black hole in the center. We want to measure the stellar kinematics near the black hole. So now we're changing scenarios a little bit. So this is good. This picture is good for one black hole, or really a big black hole. But if I have a black hole is, say, 10 to the 6 solar masses. Maybe it's 10 to the 9 solar masses. It lives in a halo that's like 10 to the 10 solar masses. So if I got a 10 to the 6 solar mass black hole, the halo is like 10 to the 10 solar masses. It's a lot bigger. So even though there's a massive black hole at the center of the galaxy would continue just fine without it. We're not orbiting the black hole, it just happens to be at the center. That make sense? Yeah.
And isn't there like a supermassive black hole at the center of many galaxies?
Yeah,
Or,
pretty much all of them.
like why is it?
Yeah.
Why is it there? I don't know.
That is a very good question, and I don't know. That's really the answer. So I'll flesh out. I don't know a little bit more as we go on. But there's this weird relationship. So if I look at the mass of the bulge, I'll come back to this. If I look at the mass of the bulge, and the mass of the black hole, they're positively correlated with each other, but there's some scatter. So bigger galaxies have bigger supermassive black holes. So what can we do with this? So a star out here doesn't care about that black hole, because there's 10 to the 8 solar masses of crap between it and the black hole. That makes sense? Stars far out don't care, even though they're in the bulge of the galaxy. So now this is it. Let's say this is a disk galaxy. Elliptical galaxies have the same problem, but a star here does. I just showed you a movie of stars that really care about their black hole, right? So this guy clearly orbiting the black hole. When it's really close, they're definitely in orbit around the black hole. The things that are further out are not. So my galaxy has a velocity dispersion. So all of these stars in the bulge have a velocity dispersion of sigma. And the book defines this quantity, RBH equals G MBH over sigma squared galaxy. This is kind of a strange concept, and he doesn't really back it up very well. So what are we looking at? So I know that the stars in the galaxy in the bulge have sigma bulge squared equals G M bulge over R star, or R bulge, right? So I know that the stars in the bulge basically behave like this. I also know, because when you're in orbit around a black hole, you're going to be basically Keplerian dynamics. So I know the same thing is true for stars that are near the black hole. I have the same behavior. The sigma squared of the stars is G times the mass of the black hole over R. So I've got these two signals. One is, so let's look at, this is R, and this is my stellar velocity. So I have a whole big mess of stars, because I have 10 to the 9 stars, or 10 to the 10 stars, maybe 10 to the 11 stars, buttload of stars, and they're all doing random things randomly around the galaxy. Now on the inside, right at the center, I have a black hole, and I have the stars that are in orbit around the black hole that are doing that. They're doing this. So as they get close to the black hole, the velocity goes up, right? Because GM over R. But I have all of the mess of the galaxy that I have to see through. So what I need to be able to do is I need to be able to resolve this region. So I have to be able to resolve this region. So this RBH is a resolution criteria. I have to be able to see this. So RBH is the mass of the black hole divided by the dispersion of the galaxy bulge. That gives me how close into the black hole I have to be able to see the motion of the things around the black hole. That make sense? So I have, it's kind of like a Where's Waldo So I got to be able to see well enough. Like if you can't resolve any of the things in the picture, then you can't find Waldo. But if your resolution is good enough, then you can find Waldo in the craziness. So the black hole is going to make much larger velocities than the bulge is going to, because you can get really close to the center of the black hole. You can't get close to the center of the bulge. It's stars that are spread out. There's not a center for the bulge, but there is a center for the black hole. So if I can resolve this RBH, that gives me a resolution criterion. So that gives me an angular resolution criterion, theta BH, which is this R divided by the distance of the galaxy. That's straightforward. That's just geometry. The angular resolution is what the telescope needs. So what does this look like? So here's M87, no, M84. And this is what, I think this picture is actually sideways. So the dust lanes are going to the left and right here, but they're going up and down here. We just rotated the picture. So what we do is we take a long skinny slit and we put it across the black hole. So the long skinny slit goes like this. So what that's going to do is it's going to cause a diffraction pattern out to the sides, which looks like this. So the stuff that's bent to the right more is redder, the stuff that's bent to the left more is bluer. And you can see that we have going down, we have some crazy madness, and then we get the velocities get very large, and then they get very large going in the other direction, and then we have our crazy madness. So why do they get very large in both directions? Because now they're close to the black hole, so their velocities get much larger than they would be for the bulge. So we can fit a line to this, and then we know that v squared equals gm over r. So we can just fit this curve to the light, and then we can measure the black hole mass. So this is the first way that black hole masses were really measured. Supermassive black hole masses were really measured here.
Yeah, the galaxy doesn't orbit around the black hole. What holds it together?
It's gravity. Uh-oh. Oh, fart. Do you have a power cord?
Mm-hmm.
Thank you. I totally forgot. So the gravity of the whole thing. So that's a really important question. Thank you very much.
Sorry, I have like these two cords that they have the iPhone charger and they look the same. So
Oh, I
I
know.
thought like they were both.
They would make everybody's life easier if they just use the same charger.
I'm sure soon they will.
Thank you very much. I appreciate it.
If they use the same charger, then they get less money.
I
People
know.
have to buy
They
all
started
the
charging for this cord.
Yeah.
Like you can buy the brick and the cord separately. Fucking capitalism. Anyway, so what holds the whole thing together? Each star in here. So, okay. Poisson's equation says that del squared phi equals 4 pi g rho. Right? So this is a statement of gravity. So this is how we find the gravitational potential phi from the density. This is just saying that U equals G M M over R, but for things that are more complicated than a point. So this is a linear function. So if I have, so rho is the mass. So it's density, but just think about it as mass. That's mass. So rho is the mass, and if I have two masses, I can add my two masses together, and I get two potentials. So to get I add my two potentials together. They separate. So I can think about the potential from the black hole and the potential from the bulge separately. And then I've got VT, the velocity equation is minus grad phi, probably plus some other things, but this is just saying that F equals ma. So this is the acceleration, and this is the gravitational acceleration, is just grad phi. So I have this relationship between velocity and potential, and the stars just have a party and find some potential and some velocity distribution where they agree. And phi comes from all of the stars, from density. Their velocity comes from phi. The density comes from just how close they are. There's another equation for that I'm not going to write down. So all of the stars hold each other together at this scale of a bulge. So the stars just have gravity, and they're all pulling together, so they're all holding together. There's also a black hole at the center. It has to be there, because it's got to fall to the bottom. But it is not what's holding the things together. It's just the stars themselves, because there's a lot more stars. Does that answer your question? Yeah. Okay, so from this, we fit this curve to these guys. So you can see the dispersion of the galaxy is the thickness of the line here. Does that make sense? The velocity dispersion of the galaxy is the thickness of that line. The velocity dispersion around the black hole is the thickness of this wide part. That gives you the velocity for the black hole itself. So we can do this a couple of times for a couple of different galaxies. There are about 30 galaxies. Oh, let's put the camera on the right spot. So here is one that used HST. So Hubble is good for this because Hubble doesn't need adaptive optics because it's above the atmosphere. Here's M87. I'm going to talk about M87 a couple of times. So this is a huge jet of stuff that is getting squirted out of the black hole. This is 5,000 light years long, and it's very straight. It's weird. There's a lot of things like this. Jets come out of these things. They just have to shoot stuff out. Oh, and the radio jet's even bigger. So we can play this same stunt where we put a slit across the top and we measure the mass of the black hole. So here's the center of that. This is the H alpha image. H alpha measures just the hydrogen. And here's what the velocity data looks like. And this gives us a mass of 3 times 10 to the 9 solar masses. We'll measure this guy again and get the same mass in a second. Let's see. This galaxy also has, oh no, this one's cool. Because this one has a maser. Did you know that there are lasers in space that just make themselves? They're called masers. They're not actually lasers. They're masers because they're in the microwave, but other than that, the physics is the same. Well, let's talk about what. Do I have time? Yeah, I got time. This is a day of miscellaneous awesome things. Masers aren't going to come up again, but I'm going to talk about them just because they're interesting. So, what's a laser? How's a laser work? Do you know? What's it stand for? What's that?
Photons like packed together.
Uh-huh. It's good. That's a good bit. Do you know what it stands for? Yeah. You're right. Light amplification. That's the first bit. Light amplification. By stimulated emission radiation. What's stimulated emission? Stimulated. That's why you don't remember.
Like something and like the electron light come out or something. No.
Too generic. Yeah, you excite things and light comes out, but there's a lot of ways for the light to come out. So I have a hydrogen atom. let's say it's in its first excited state. How does it get to the lower state? By emitting a photon. So there's 3 ways for this electron to get to the lower state. It's going to emit a photon in all of them, but oh, and this is one. This is a better lecture if I have my notes up, but I didn't. But I forgot to do that. So it can spontaneously fall. So after a time, that electron will just get sick of being in that excited state and fall down to the ground state and give off a photon. That's spontaneous emission. That sometimes takes a long time for some states. The second way is collisional. If I hit this atom with something, I can excite that electron to a higher state, or I can knock it into a lower state by kicking it with another atom, or stimulate it. Kick with a photon, or something like that. They're stimulated. This means that you get kicked by a photon. So a photon can come along, and if the photon is the same energy, it can induce the electron to fall to the other state by just going by. And then I have 2 photons, and they're in phase, and that's what makes it special. So when I stimulate the emission, I get coherent radiation, so the 2 photons come out in phase. So how does a laser work? So when a laser, I have a cavity, and I don't always need a cavity. You can make solid state lasers that don't have a cavity. With a bunch of atoms, and I kick them all into the upper state. Whatever that means. I have a bunch of things that have 2 states, and I kick them all into the upper state by exciting them, by getting them hot. And then I send a photon from this side, and it knocks down all of these guys like a domino train, and then I have a buttload of photons that are all in phase with each other. Does that make sense? And then I have a lot of photons. Then you can let them rattle around and pick up photons, and then they come out, and you have a bunch of photons that are all in phase with each other. Because the light gets amplified by the stimulated emission radiation. So the stimulated emission says I get a photon that hits this guy, so I get 1 photon and it hits this one, which gives me 2 photons, which can hit this guy and this guy. That gives me 4 photons, which I can hit the next one, and I didn't draw 10 to the 20 atoms because I'm bored. But it does that a lot of times, and then you have a lot of photons that are all coherent. Makes sense? So all I need is a bunch of stuff that's in the excited state. So if I take a cloud of water gas, there's lots of those. Water's really common. If I take a cloud of water gas and I shock the crap out of it, like crushing it with a black hole, it'll do this. But it does it in a really funny way, because this is clearly, you've got to line things up just right. So it doesn't really want to happen all the time, but it happens. And it happens in a way where it makes these point sources that are fractal, because this is a turbulent cloud of violence. It just got beat up so that everything's excited. You get these fractal clouds that are incredibly small and very bright in the radio. So a maser is microwave amplification by stimulated emission radiation, which actually was invented before the laser was. The important bit is they're a point source, which means that I don't have to resolve the object itself. It doesn't have some extended space. So when I see that object, I know exactly where it is, even if I can't resolve it. So we can use these masers to measure the dynamics of the disk around the black hole, because the disk has these masers in it, and some of them are coming at us and some of them are moving away, and we can measure the velocity, the mass of the black hole. This also needs VLBI, because you have to be able to resolve where the masers are around the disk. But we can use these things that are just spinning around the disk to tell us what the mass of the black hole is. Where's my pointer? How am I on time? I have a couple minutes left. Okay. This was one of the most exciting things that I've seen because I didn't think it was going to work. I really didn't think LIGO was going to work. So they've got these mirrors. One of them is in Louisiana, kind of far up, and they can see the storms on the Gulf of Mexico from the middle of Louisiana by just measuring the vibrations of these ultra-sensitive mirrors. So they have these mirrors that are hung in this really complicated way so that they are isolated from all the vibrations around. It's a long 4-kilometer tube with a laser inside. There's a big sign that says, "Please don't shoot the laser," and it's full of bullet holes because it's in Louisiana. So anyway, so what does it do? It measures the length of these two arms, and black holes, when they spiral in, so what happens? So you've got two black holes and they're rotating around each other, and they're giving off gravitational radiation. And as they give off that radiation, gravity energy leaves the system, so they get less bound. Gravity energy inside goes down. Remember, gravity's negative, so gravity energy going down means it's actually bigger, but negative. So things start spinning faster because you've got more energy. They got more kinetic energy because they went down this negative potential well. So they spin faster and faster and faster until they collide with each other, and then they stop. So this happens. So this is the strain. So this is the amount of deformation of the two arms of the LIGO detector. And this is one in Louisiana, and the other one is in Washington State, way in the middle of nowhere in Washington. Why do you need two? Because if I see a weird signal in one, it could just be a truck hitting a tree or something. But if I see the same weird signal at the same time in both the detectors, then A, I can measure the speed of gravitational waves. It's C. And two, I know that it happened. Like if I see the same signal twice, then we know that it actually happened and wasn't just noise. So we saw the same signal in both the detectors. And this was actually an engineering run before they actually turned it on for the first time. They were just checking to make sure that things work. And they saw a black hole merger. It was really weird. All the press releases were like, as they were turning it on, they were like, "Yeah, we're pretty sure we're going to see something. We're pretty sure we're going to see it." And they had already seen something, and they were working on the data. But anyway, it was very fun. So we have this strain, and you can see the frequency goes up, whoop, as the two things spiral. And this is audio frequency; you can hear it. It goes whoop. Let's see. How much did I said all that? Yeah. So at its most sensitive, LIGO will be able to detect the change in distance between its mirrors to 1/10,000th the width of a proton. This is like measuring the distance to Proxima Centauri to within the width of a hair. It's an unbelievably tight measurement. So it's very cool. And there are several more. So there's now one in Italy. There's going to be a couple in India. So we're going to have more and more and more of these LIGO interferometers. Yeah.
I'm kind of curious, how big were the variations from the data? Was it because you can measure down to 1/10,000th of a proton, and how big were these?
10 to the minus 21. Now I don't know what units that's in, but it's a really little number. I'm pretty sure that's the relative difference. It's arm length A minus arm length B over arm length A is 10 to the minus 21. And that's over 4 kilometers. So what's 10 to the minus 21 of a kilometer? Not much. So very, very, very little. But they do it by measuring the brightness. They measure the interference pattern, not the actual length of the thing. So all they're doing is beating down the noise. So the things, the mirrors vibrate like crazy from all of the other stuff that's going on. So, okay. Other things. Am I running out of time? I am running out of time. I'm going to talk about the last thing. This is the last thing in my... Oh, yeah. No, it's not. Okay. This is the last one. This is the most recent measurement that's an actual measurement of a black hole. And this is the actual black hole. This is the event horizon of a black hole. This is also something I never thought I was going to see. And yet somebody smarter than me figured out a way to do it. They use this event horizon telescope where there's... These are all the telescopes that they use. They use one on the South Pole. They use one in Chile. They use JCMT. They used Hat Creek. They used one in... that's not in that spot. I think that's in... Should be over here. Anyway, they use Green Bank. They use a bunch in Europe. And they make one big-ass telescope. And they use that to measure this. So this is... Oh, and this is the jet. And then you can zoom in on the center of the jet to see the black hole in the center. This is, they've done 2 of these. One for M87, which is a, oh, and they measured the mass to be, again, 3 times 10 to the 9 solar masses. So they did M87 before doing Sagittarius Star, even though Sagittarius Star is closer. Because M87 star is the same size as Sagittarius Star on the sky, even though it's a million times further away. It's a billion times further away. It's a million times further away, but it's a million times bigger. So it's the same size on the sky. We don't have to look through the whole galaxy to see it. So we saw this one, and then they saw, and I haven't put them in this slide deck yet because it just happened. They saw, they've measured the black hole around, or they've measured Sagittarius Star with this as well, and it's exactly as big as you think. But Sagittarius Star is weirdly more dynamic and active than M87 Star for reasons that I don't really understand yet. So it's a harder picture to do. So we can just measure the black hole. And then how massive is this black hole? You can just read it off of this picture. It's this massive. Right? Because that multiply that by 3 kilometers and the distance, and you have a massive black hole. Yeah.
The event horizon and the Schwarzschild radius, are they like the same?
Yeah, the event horizon is at the Schwarzschild radius. Let's see. Anything else? It's probably time to stop talking. Let me... Okay, this slide deck is packed full of good stuff. I'll put it up in a minute. This is the last thing that I want to say is this black hole bulge mass relationship. So there's a relationship between the mass of the bulge of a galaxy and the mass of the black hole in the center. The mass of the black hole is 10 to the 8 times the velocity dispersion to the 4th. I have no idea why it's to the 4th. None. But there it is. I don't really know why this relationship works, because the black hole mass doesn't care about the galaxy mass. Shouldn't, but they're formed through the same channels. So in the process of building the galaxy, you build the black hole too. So black hole mass is proportional to the galaxy velocity dispersion to some power. Has to do with the density, I think. So anyway, that's all I got for today. I'll see you guys Thursday.